Okay, so weight we can find out by using the formula for density, which is equal to mass upon volume. So first calculate the mass, which is density into volume. Okay, so density, this is equal to 700 kg per meter cube into volume of that liquid is 1 liter. Okay, so which is equal to, so this is 1 liter. So in the SI unit, this is 10 to the power minus 3 meter cube. Okay, so mass you will get as 0.7 kg. Okay, and just multiply this mass, so you will get the weight. So weight, this is equal to W, this is mass into G, so it is 0.7 into 9.81. Okay, so this is equal to, so it is 6.867 Newton. Okay, so this is the weight of 1 liter petrol. So the question was find the density, then the specific weight, and the weight of 1 liter of liquid. Okay, so now we can calculate the specific weight as weight of the liquid. So weight of the liquid is 6.867. So this is in Newton, and its volume is 1 liter. Okay, so it is a 1 liter. So this is equal to 6.867 liter means 10 to the power minus 3. This is meter cube, and this is Newton. Okay, so always remember, for specific weight we need the unit as Newton per meter cube. Okay, so here you will get the answer as, just take 10 to the power minus 3 in the numerator. So this is equal to 6,867 Newton per meter cube. So this is the specific weight, note, or weight density. Okay. So for this convergence, you must have the knowledge of the fundamental properties of the fluid. Okay. Okay, so now we will see the classification of the fluids. So first type of fluid is ideal fluid. So an ideal fluid is incompressible. Okay, that means you cannot compress the fluid, and it is an imaginary fluid that doesn't exist in the reality, and also it doesn't have the viscosity. Okay, so for the ideal fluid, its viscosity, it will be 0. Okay, and it is incompressible. So this is an imaginary fluid. Second is ideal plastic fluid. So for the ideal plastic fluid, when the shear stress becomes proportional to the velocity gradient and more than the yield value, the fluid is said to be ideal plastic. Okay, so we will see this with the help of one graph. Then real fluid is fluid having the viscosity, real fluid. Okay, Then we have the classification depending on the Newton's law of viscosity, which is the Newtonian fluid and the non-Newtonian fluid. So fluid obeying the Newton's law of viscosity, they are called as the Newtonian fluid, and fluid doesn't obey the Newton's law of viscosity are the non-Newtonian fluid. Okay. After that, we have the incompressible and compressible fluid. So incompressible means when the density of the fluid remains invariant with the application of external force. So it is said to be incompressible. Okay. So in the incompressible, we have the water. Okay. That means if you apply the force or the pressure, the density will remain constant. There is no change in the density. They are called as incompressible. Okay. And for the compressible fluids, when the density of the fluid varies with the application of external force, it is called as a compressible. Okay. So all the gases, they are compressible. Okay. So incompressible fluids, they are used in the hydraulics. Okay. So hydraulics means in the JCB, hydraulic cylinder, then hydraulic jacks, then power press. Okay. So here you can see the application of incompressible fluids. So we generally use the oils to transmit the pressure. Okay, so here with the help of this graph, we can see the classification of various fluids based on the Newton's law of viscosity. Okay, so here we have the rate of deformation. So this rate of deformation, it is given as a du by dy. So basically this graph, so it is for du by dy on the x-axis and the shear stress, that is a tau, on the y-axis. Okay, so now just refer the Newton's law of viscosity. Tau is equal to mu into du by dy. Okay, so here we will get mu is equal to tau upon du upon dy. This is the rate of deformation or velocity gradient. So what is Newtonian fluid? So for a particular fluid, if you observe its deformation with respect to the shear force or shear stress, then you will get such a straight line. Okay, that means if you gradually increase the force on that liquid or the fluid, then it will deform continuously. Okay, so you will get this straight line. So this is called as a Newtonian fluid. Okay, so for the Newtonian fluid, the slope of this line is nothing but the viscosity. Okay, so here you can see the mu is nothing but tau upon du by dy. So this is nothing but the slope of the graph. Okay, so the slope of this graph, it will give directly the value of viscosity for a particular fluid. Okay, so the fluids which follows this Newton's law of viscosity. So here the example is water, then petrol, okay, then oils. So these are the common examples for the Newton's law of viscosity. Okay, or Newtonian fluids. Now the fluids which doesn't obey the Newton's law of viscosity, that means the graph is not straight line. All these are non-Newtonian fluid. Okay. Now here you can see the non-Newtonian fluid. Okay. So in the non-Newtonian fluid, we have, so here this is the first type, which is the Newtonian fluid. Okay. And the second type is a non-Newtonian. So in the non-Newtonian fluid, again we have the types as the shear thickening fluid, Okay, and shear thinning fluid. Okay, so let us see what is difference between these two fluids. So this is non-Newtonian fluid. So I hope you understood what is meaning of Newtonian fluid. So water, kerosene, then petrol, then oils. These are all Newtonian fluids. They obey the Newton's law of viscosity. Okay. Non-Newtonian, we have first type, which is a shear thickening fluid. Okay. So what is meaning of shear thickening fluid? As we increase the shear force on the fluid, so it becomes thick. Okay, as we are increasing the shear force or the shear stress. Okay, so you will get the graph for such fluid. So for Newtonian fluid, we have the directly proportionality, so we get the straight line graph. Okay, for shear thickening fluid, if you increase the shear stress, then there will be less deformation. Okay, so their graph will be, so less deformation means the graph will be like this. Okay, so here you can observe, if you increase the shear stress, that is a tau value, okay, the deformation will be decreasing. Okay, so therefore you will get such type of graph. So in this shear thickening fluids, we have the examples such as the cornstarch solution in water. Okay, so this is the very common example for the shear thickening fluid. Okay, or the example of sand. Okay, so sand in the liquid. So these are the shear thickening fluid. So I will show this effect. If you increase the force, okay, actually it becomes hard. That is called as shear thickening. So just I will share the video. So here you can see the difference between the Newtonian and non-Newtonian fluid. Okay, so here we have taken an example for honey. So it follows the normal law, Newton's law of viscosity. Okay. Okay. Now this is the cornstarch solution. Okay. So cornstarch solution in the water has a strange behavior. Okay. So this is the low force. Okay. So that means low shear stress. Okay. So at the low shear stress, it behaves perfectly as a Newtonian fluid. Okay. So there is a deformation, but when we apply very large force suddenly, so now you can see it becomes suddenly hard. Okay. So there is a change in the viscosity when we are applying the high value of the force or high value of shear stress. So this is called as a non-Newtonian fluid. Okay, so with this video, you must have understood the difference between Newtonian and non-Newtonian fluid. Okay, so constant solution is a very good example for the shear thickening fluid. Okay, the thickening means it becomes hard when you increase the shear stress value. Okay, so when you hammer that fluid, it becomes hard. So here on the graph, so you can see here at the low value of stresses, okay, low value of force, it is having the low viscosity. Okay, so this slope is small. Definitely it will have low viscosity, but suddenly if we increase the value of stress, if you select this point, okay, so it will have the large slope, okay, and therefore it will have the high value of viscosity. So it behaves as a hard fluid. Okay, so this solution, constant solution in the water, it is the shear thickening non-Newtonian fluid. Okay, next type we have the shear thinning fluids. That means if we increase the shear stress, okay, then fluid becomes soft. That means it will start flowing. Initially it will be hard at the low value of the shear stress or shear force, and when we increase the value, then it will start flowing. Okay, so in the shear thinning, so we have the examples for the shear thinnings are the wall paints, okay, then some polymer solutions. So you can observe when we have the paint in the container, okay, so here we are not applying any force, so it appears as a thick, okay, at the low value of the forces or shear stresses. And when we start painting on the wall, okay, so actually we are applying the force on that fluid, okay, with the help of the brush. So it becomes thin, okay, and it starts flowing on this wall. So it becomes soft at the high value of the stress. Okay, so actually you get the graph like this, exactly the mirror image of the first graph. Okay, at the low value of stress, it is having the high viscosity. So you can see here the slope is large, okay, and slope gradually decreases as we increase the shear stress. Okay, so it becomes softer. So this is called as shear thinning fluids. Examples are paint and some polymer solutions. Okay, and then we have, so this is also called as a pseudoplastic. So these fluids, so they are called as a pseudoplastic. And the shear thickening fluids, they are called as a dilatant. Okay, and next type of fluid we have, just we will finish this. This is called as a Bingham. So this is Bingham plastic fluid. Okay, so here you can observe one strange behavior of the fluid. So this is the shear stress and this is the rate of deformation, which is at u by 2. Okay, So up to certain value of shear stress, okay, the fluid will not start motion. Okay, so it will behave as a perfect solid, and after this point, that is particular value, it will come into the motion. Okay, and then after that it will behave as a perfect Newtonian fluid. Okay, so this is the strange behavior, and this is called the Bingham plastic. Okay, so in this Bingham plastic, such type of fluid, we have the, so here we have ketchup. It is the best example. Okay, okay, so in the next lecture I will show the video for the Bingham plastic. Okay, the tomato sauce or the ketchups, they are the examples for the Bingham plastic fluids. Okay, so today we will stop here.